Hello guys and welcome to our first lecture series, our first lecture series actually, and the first lecture of this lecture series on statistics and probability. This is material that I'm learning myself, I'm teaching it to myself because I don't find it actually, we use statistics and probability very often in research, in scientific research, and I have to learn it at some point. And well, if I'm going and I am trying to make this website and teach stuff to people, why not go full on and learn the whole thing, right? So how it works is that I am teaching myself the material. I am using a textbook from the University of Toronto, Statistics and Probability and Applications. I'll leave a link for the textbook on the page here. You can find the textbook in there. The textbook is great, has a bunch of exercises, it's very easy to understand. And I'll be inspiring from the material on that textbook to teach you guys about statistics and probability. The lesson today is about probability models. It's very simple, very beginning of probability. We'll talk about probability models, what they are, what makes them, and we'll also talk a little bit about Venn diagrams. Okay? So let's start. Hopefully this goes well. Well, probability models. Probability models, we need them to be able to mathematically study any concept of probability. You know, you can think of probability as how likely is it that it will rain tomorrow, about the weather tomorrow, for example. Will it rain, will it snow, or will it be clear? It's very hard to put math if we're just talking on this way, right? Because when we're talking about math, when we're doing mathematics, we actually need a model. We need something to work with. And this something will be our probability model. Every probability model is made of a sample space. It contains a sample space that we call S. So let's start our notes very quickly here. We're talking about probability models. Probability models, and this will be made of a sample space. So we have a sample space that we will often refer to as S. Our sample space is S, and the sample space is a set or a list of all the possible outcomes in the model that we have. Right? So if we're talking about the weather, for example, our sample space could be S, being the list of, I can do those little curly brackets, but being the list of the outcomes. It could be clear, or it could be rainy, or it could be cloudy, it could be snowing, right? Any type of weather that you can think of. This would be our sample space. S. The sample space is the list of every possibility on the model that we're trying to build, right? And we can use in a notation that we'll be using in probability for these lectures, and the textbook uses this notation as well, is little s will be a element of S. So, and we can write that as little s is an element of S, meaning anything inside of my little s is also inside of big S, the sample space, right? And the probability model also requires a collection of events, subsets of S. So let's say if our S is this here, right? It's clear or rainy or snowy or cloudy, then the events could be, for example, raining. It could be rain or snow, etc., right? So let's write an event A, for example. The event A could be clear. This is an event inside of our sample space S, right? I could have an event B, which is snowing. I could also have, for example, the event C, which is clear or snowing, right? Now notice here I'm using a comma here. This comma, let's erase this. The comma that I'm using there means or. It doesn't mean and or anything else, it's or, right? Meaning it's either clear or snowing. In this model that we have, it can't be both, okay? So up till now, what do we have in our probability model? we have our sample space S, which is either clear or rainy or cloudy or snowy. We also have events. It can be clear, snowing, clear or snowing. And all of these events are subsets or elements of S, our sample space, right? And we call them little s. Okay? Now, the last thing that we need to have a full model is a probability measurement. How likely is it that it will be raining? How likely is it that it will be snowing? And the notation that we'll be using for that is the probability of A, so the probability of it being clear. We'll write that as P of A, probability of A, and that's a uppercase P. The probability of it being rainy, right? So P of A is the probability of having a clear weather, right? Seems pretty simple, pretty straightforward, right? Now, the probability measure has to be some specific properties, right? So let's write about the properties of the probability measures. So the properties of our probability measures. So these properties will be, there are 4 of them. First, the probability measure has to be between 0 and 1. So P of A will be between 0 and 1. And we can see that as percentages, for example. If I say, for example, that P of A is equal to 0.2, that means that it's 20%, there's a 20% chance that it's clear tomorrow, right? Because A was our clear, right? So this probability can never be higher than 100%, right? Because what does it mean for something to be 110% likely to happen? That doesn't make sense, right? So the probability has to be between 0 and between 1. The second property is that the probability of nothing happening, that we will write probability of nothing happening. This is the notation that we'll have. This is equal to 0. That means there's no chance, never, nothing will happen. Something has to happen. So the probability that nothing happens is equal to 0%, right? So tomorrow, if I look out of my window and I look at the weather, it will be either raining or snowing or clear, but it doesn't make sense for nothing to happen. So the probability of nothing is equal to 0, right? Okay, then the next property is that the probability of something happening, or anything within my subspace, within our sample space, right? The probability of something happening is equal to 1. Now remember, S here, the big lower, the high uppercase S, right, is our whole sample space. So that is, it will either be clear, rainy, cloudy, or snowing. So the whole S, it's either clear or, remember, comma is or. So clear or rainy or cloudy or snowy, there's 100% chance that it will be either clear or cloudy or snowy, etc. So P of S, the whole sample space, is equal to 1. Now the fourth property is a bit more complicated to understand, but we'll get there, especially after we study Venn diagrams that I'll be introducing later. The fourth property states that probability measurements, so the P is additive. What does that mean? It means that I can add the probabilities of things to know the overall probability of it happening. So for example, here we had the event A is that it's clear tomorrow. The event B is that it's snowing tomorrow. The event C is that it was clear or snowing tomorrow, right? Now this here is true for countable and disjoint events. When I say disjoint, I mean they are events that are independent from each other, right? So this here is true for countable and disjoint events. Okay, so let's look, for example, if I have A was equal to being clear and B was equal to being snowing, now C is equal to being clear or rainy, right? This should be a curly bracket. In here, I have three events. I have the event A, the event B, or the event C. The event A and B, they are independent because it's either clear, A, or it is snowing, B. So we say they're independent. They are disjoint. Now the event A and C, for example, these are not independent because C is either clear or rainy. And event A is clear. You see, they share this possibility of it being clear, meaning that they are not fully separated from each other. So if I was to see what is the probability that I have either clear or rainy, that doesn't work, right? I can have the probability of it being either clear or snowy, but not the probability of it being clear or rainy. Do you understand what I mean? So what I mean by this fourth property, saying that P is additive, is, for example, I'll have all of these probabilities here. So there's a 20% chance that it's clear and a 80% chance that it's snowing. Let's ignore the C for now. P of A is equal to 20% and P of B is equal to 80%. Now, if I wanted to know P of A or B, so that would be P of A union B. This is a notation to say or B. So we're looking at either the event A or the event B will be equal to the probability of A plus the probability of B, which is equal to 20 plus 80%, which is equal to 100%, right? So this here is if our sample space was only clear or snowy, right? So we're not looking at the same sample space as before. But this is what I mean by the fourth property, saying that P is additive. This means that if I know the probability of A and I know the probability of B, that means that I also know the probability of either A or B, as long as they're disjoint, right? Great. So let's look at a couple of examples. To summarize everything here, we have the probability model is made of sample spaces. Let's start to highlight some stuff. The probability model is made of sample space, S, usually capital S. It is also made of events that are subsets of our sample space, right? And finally, it's made of probability measures that have four properties. The probability measure of each event is between 0 and 1. The probability of nothing happening is equal to 0. The probability of anything happening is equal to 1. And the probabilities of different events that are independent from each other can be added together to have the overall probability of that subset of S, right? Okay, so this is our probability model. A probability model has to have these three things: the sample space, events, and a probability measure for these events. Okay, so now we have a better idea of how to use math, how to talk about these things in a math kind of language for us to make calculations with it. Let's give some examples. Okay, so let's look at the first example here. An example would be, for example, if we have a candidate on election. So candidate B, candidate A, and candidate B on elections, right? There is a 80% chance that A will win, right? Okay, so what is our probability model here? Where our sample space will be made of two events, right? It's either A wins or A loses, right? We know that the probability of A wins is equal to 80%, so 0.8. What is the probability of A loses then, if we know that the probability of A winning is equal to 0.8? You can pause the video and try that if you want. I'll give the answer right now. That's pretty straightforward, right? I think we all have some kind of intuition for this, is that if 80%, there's an 80% chance that A wins, then the probability of A losing is equal to 20% or 0.2. How did I do that? Well, I know that my S is A wins or A loses. My sample space is either A wins or A loses, right? And I know that the probability of S is equal to 1, right? Because I only have two events, I can say that my probability of S is equal to the probability of A wins or union A loses. And as we've seen with the fourth property of probability measures, this here is equal to the probability that A wins plus the probability of A loses, right? And as I've shown here on top, P of S is equal to 1. And we know that the probability of A wins is equal to 0.8. And we don't know what the probability of A losing is. But then we can just isolate, right? You can just have the probability that A loses will be equal to 1 minus 0.8, which is equal to 0.2, right? This is the math way. So I made all of these calculations. I made this long line of equations because I wanted to show you that now I have a way of playing with these ideas that we had in our head, but with numbers now. We can do math with those things because of the probability model that we just made. Okay, now let's talk about Venn diagrams. Venn diagrams. Venn diagrams are very, very useful when we're looking at probability and trying to have a more visual or intuitive way of understanding the probability models that we have. So a Venn diagram, you guys might have heard of it before, might have seen it before. It will be something like this. If I have the sample space S, I will be showing the sample space S as a square. And then I have the event A that I'll be showing as a circle inside of my subspace, of my sample space S, right? So I have the event A inside of my sample space S. And I can say that A is a subset of S. And I do this with this kind of funny looking C. That means A is a subset of S. Right? You can see that everything that is in my A here is also inside of my S here. Right? Great. Let's get back to the colors that we had before. Great. The other thing that we have here is what we call a complement. A complement, and we write that the notation that we'll be using is A subscript C. That means anything that is not A but is still in the subset S. Anything that is not A will be a complement. So anything outside of this circle here in our Venn diagram is a complement. Okay. Let's say now that I had the event A and B, and that A and B had an intersect. So here's our subspace S, our sample space S, and I have the event A and I have the event B, and A and B intersect at this point here, right? Yeah, okay. How will we call this location where A and B intersect? Well, this will be A intersect B, and I'm using this weird looking upside down U to refer to as intersect. That's the notation that we'll be using. So A intersect B, right? A intersect B. That's the location in the Venn diagram that A and B share. So the space in our sample space that is shared by both the events A and B, right? So for example, what do I mean by this? Great, we're drawing and stuff, but give me an example. Let's go back to our example of raining, snowing, about the weather, right? Let's say that A is equal to raining or snowing. B is equal to clear or snowing, right? This is A and B. Now A intersect B will be either, there's no either, it's just snowing. It's the event, the subset of S that is shared by both A and B. So A intersect B will be snowing, right? Let me move this a little bit to the side. This is an example of this A intersect B, right? Okay, finally, we have another notation that we will call A union B. So the union will be and. So that's or. I'm sorry. Union is or. So this is the same as A union B, which will be either A or B. Anything that is either on A or B. So our A union B is everything in here. I can draw this. This whole thing here is A union B. A union B. Right? Great. Now that we know these notations, I can write a couple more stuff. I know what is A complement, and I know what is B complement. Anything that is not on A, anything that is not on B. What if I have A union B complement? That's anything that is not on A or B. It's neither on A, either on B, right? So our A union B complement, that will be anything here on the purple space that I'm coloring now, right? So all of these, let's choose a new color here to try to match that with our purple. That's A. That was not a good color. That looks like our red, right? What color will I pick? This is hard. More colors. Here we have some purple here. It's A union B complement, right? Great. Now, what if we have A complement intersect B? What does that mean? Let's take a look. So A complement intersect B. In our Venn diagram, A complement intersect B would be anything that is not on A but is on B, right? So let's try and draw that. If we have our sample space S, we have A and we have B. A complement intersect B would be this blue region here. Anything that is not on A but that is on B, right? So A complement intersect B. Finally, let's look at the situation where A and B are disjoint. What does that mean? Again, it's that they are independent from each other. In that case, if A and B are disjoint, then our Venn diagram would look something like this. We have our sample space S, we have the event A, and we have the event B, and they do not intersect. They don't intersect because they are disjoint. That's what I mean when I say disjoint, right? And so if we have that, then the probability of A intersect B would be equal to 0, right? But the probability of A union B would be equal to the probability of A plus the probability of B, as we saw in the fourth property of probability measures, right? We showed this here. It's our fourth property of probability measures right here, right? I have the exact same formula written here, right? All right. I think this is enough. This is enough for now. This is a long enough lecture. I hope this was useful for someone on the internet. I hope you guys had a good time learning about probability models. If you have any questions, any comments, please feel free to leave them down. I will make sure to read them all and answer any questions. Thank you very much, and I'll see you next week. Cheers.